All right, so now we're going to pick up on the empirical rule. Now, the empirical rule is saying that if a distribution is roughly bell-shaped, the other word for that is normal, then the following things are true. Approximately 68% lie within one standard deviation of the mean, 95% lie within 2 standard deviation of the mean, and 99.7% of the data lie within 3 standard deviation of the mean. So note, we can only use the empirical rule based on sample data with, we can also use the empirical rule based on sample data with X bar and S. It doesn't have to be mu and sigma. If a single data value lies beyond 2 standard deviations away, it's considered unusual. If a range of values is less than 5%, that's also considered unusual. And I put this extra note in, and I guess I could put them right up here somewhere. Here. The empirical rule only works if the data is normally distributed. Okay? If it makes this lovely picture right here, that's called the normal distribution. If it doesn't make that picture, you're out of luck, right? This, you'll have to do something else called Chebyshev, which we will learn in a couple pages. Okay? And then I wanted to add something to these pictures because it's a good picture, but I want to make sure that you understand that this little side keeps going. It doesn't stop at 3. It keeps going and going and going. And it keeps going that whole way. So you can get 4 standard deviations away, 5 standard deviations away, 6 standard deviations away, and so on. By the same token, you can get that many standard deviations away on the low end. So you could get 3, 4, 5, 6 standard deviations away on the low side. That tail, all of it, all 10 standard deviations away, 11 standard deviations away, and so on, all adds up to 0.15%, right? And then same with this whole tail makes 0.15%. And then in the middle, you've got your 68. See, 34 and 34 make 68. And since it's normal, it's half on one side, half on the other. And then you got 95 within 2. So that gives you 13.5 plus 34 plus 34 plus 13.5 all adds up to 95, and so on. Now, what does the whole curve have to make altogether? 1, right? That'd be a good point to mention as well. I will put it right up here. Hold on. There we go. I added in that little point. So the area under the whole curve adds up to 100%, right? And then this whole thing only works if it's normally distributed. Beautiful picture like that. And these little guys in the tails, past 2 standard deviations this way, past 2 standard deviations that way, so past this marker right here, are considered unusual. Fabulous. All right, now that's going to be true for all normally distributed things. So we have a survey conducted by the National Health Center for Statistics. Sample mean height of women in the U.S. is 64 inches with a sample standard deviation of 2.75. Assume that heights of women are normally distributed. Construct a normal distribution with parameters and proportions labeled. All right, hold on. I'm going to have to do this and come back. And there we have it. So I did this in Minitab. This is the program Minitab. You don't have to worry about it. You can just draw it by hand on your notes. But so the middle is 64 because that's the center, right? And then we have each of these is 2.75 away because the standard deviation was 2.75. So 2.75 and then another 2.75 and then another 2.75. You add them all on right there. And then you go the other direction, subtract 2.75, subtract 2.75, and so on. And then you put in all your percentages. All right, so let me copy and paste this into the other. There we go. Boom. This is going to be annoying because it doesn't. Minitab and Microsoft Word don't like each other very much. All right, so believe it or not, once you have this down, the hard part is done because you can use the percentages and the graph in order to answer all the questions. And for the record, I don't know if I mentioned this before, but you don't have to memorize stuff like this. You have, on the final exam and on the midterm exam and on any other exams, you have a sheet of notes that you can create of your own creation, right? So it would be probably a wise move to have pretty much this whole page somewhere on your notes, right, in miniature form, but put it on there. You don't have to memorize this stuff. You have to know how to use it and what we're talking about. So that's way more important than memorizing any of this. So don't worry about memorizing. Worry about being able to explain and answer questions. Okay? All right, so the first thing I ask is what percent of women are between 64 and 60.9.5 inches? Okay, well, 64 to 66 is right here. That's 34%. Plus the next group from 66.75 to 69.5 is 13.5%. So altogether, that makes 47.5%. Done. Next. What about women that are taller than 69.5? That would be 2.35% plus 0.15%, which makes 2.5%. So only 2.5% of the American women population, American women, are taller than 69.5 inches. All right, what about women that are taller than 64? Well, I'm going to give you a hint on that one. You don't really need to do any work. All right, look, 64 is the middle, right? And the whole curve makes 100%, right? So shouldn't it be 50%? Exactly. Now, if you want to, you can type 34% plus 13.5% plus 2.35% plus, oops, that's plus 0.15%. If you want to do it that way, that's fine. But you could honestly do that one without any work because it's kind of obvious. All right. What about the next one? What percent of women are between 61.25 and 72.25? All right. So you start at 34% for the first section, plus another 34% for the next section, plus 13.5%, plus 2.35%, and then you stop. See, 72.25 is right here on the right. There's more, right? Because there are women that are taller than 72.25, but we only want between those two numbers. So we're not going to get to women that are 74 inches tall and stuff. Right? We stop at 72.25. So you add up this percentage in this first section plus the percentage in the second section plus this 13.5 plus this 2.35, and you're done. Right? You don't keep going. And that altogether makes 83.85, oops, if I could type, percent. Now, are any of the results above considered unusual? Why, yes. Yes, they are. And it's this one right here for number C, or letter C, excuse me, number C. So, yes, being, taller than 69.5 inches is unusual because it's less than 5% of women are that tall. Okay? By the same token, I'll write that. By the same token, women that are shorter than 58.5, 58 inches are also unusual. Again, less than 5%. Okay? Or more than 2 standard deviations away is another way to think of it. Gosh, I can't type. Okay, so if you're a woman that's in either one of those tails, you're unusually tall or unusually short, right? Because you're more than 2 standard deviations away. Matter of fact, having such problems. There we go. So if you're out here, you're past 2 standard deviations away. See, 1 standard deviation is 66 and 0.75. 2 standard deviations away is 69.5. So being past that is being past 2 standard deviations. So you could say also, because it's past 2 standard deviations, right? Or hold on. It's less than 5% when women are that tall, or because women who are that tall are more than 2 standard deviations from the mean. Away, I should say. Are more than 2 standard deviations away from the mean. There we go. I can say that in English. All right, there we go. All right, last but not least, let's talk about Chebyshev. Now, Chebyshev's inequality is what you do when your data set is not normal. Okay, so that's why we need it. We need it because not all data sets, here, let me type this up. Hold on one sec. So the empirical rule only works, I said it before, but I'll say it again, it only works if it makes this beautiful picture. If it doesn't make this lovely normal distribution, i.e. bell shape, then you're in trouble, right? If it's skewed right or skewed left, that's when Chebyshev comes into play. Okay, so if the distribution is skewed, this is your formula, 1 minus 1 over k squared. That's the least amount that would lie in between that many standard deviations away. So what am I talking about? Let's try it. So let's try k equals 2. Oopsie. K equals 2. Okay, so according to the formula, it's 1 minus 1 over k squared times 100%. Okay, that would be 1 minus, well, let me make this bigger so you can see it. 1 over 2 squared times 100%, which is 1 minus a fourth last time I looked. 1 minus, my fingers are typing too fast. All right, then times 100%, which is equal to 3/4, right? 0.75, 0.75 times 100%. Oops. Sorry, I'm trying to make this so you guys can see it all. All right, there we go. 0.75 times 100%, which is 75%. So according to Chebyshev, 75% have to lie. So at least 75%. In fact, I'm going to type this in. At least 75%. Hold on. There we go. So according to Chebyshev, at least 75% of the data are going to lie within 2 standard deviations if it's skewed. Actually, it'll be at least that much. So even if it's not skewed, it'll be more than that, like it's 95% if it's normal. Now, what if it's 3 standard deviations? It's the same formula, it's just with 3 in there. So it's 1 over 3 squared, which makes 1/9, and that makes 0.88888 repeating, which means if it's skewed or if you don't know what the shape is, then at least 88.9% lie within 3 standard deviations, maybe more. Heck, if it's normal, it's 99.7, right? Okay. So suppose a new electrical volt generator produces voltage amounts with a mean of 125 and a standard deviation of 0.3. Using Chebyshev, what do we know about the percentage of volts that lie within 3 standard deviations? At least 88.9. You know what? Let me type this. Hold on. All right, there we go. So notice we have to use Chebyshev in this problem because we are not told anywhere in there that it's normal. Since we don't know the shape, we have to go with Chebyshev, which is weaker than the empirical rule. If we knew empirical rule, things would be great. Then I found what 3 standard deviations away was. I took 125 plus 3 times the standard deviation. That got me that number, 125.9. And then I minus 3 standard deviations. That got me 124.1. And Chebyshev says that at least 88.9%, because we found that with this formula, of the voltage amounts outputted from the generator are between 124.1 and 125.9 volts. There you go. Right? So that would always work. That 88.9% will always work for 3 standard deviations away for any distribution. It might be higher than that, but it can never be lower than 88.9% for 3 standard deviations, no matter how skewed the distribution is. By the same token, no matter how skewed, it'll always be at least 75% within 2 standard deviations. It might be more, like 95% for empirical, but it can never be less than 75%. All right, we're done with section 3.2. I'll see you back here for 3.3.